Hardly any process is so decisive for life on Earth as photosynthesis. But how does it work in detail? When sunlight hits a leaf, a molecular dance begins that is the basis for almost all life on Earth. If we could watch this taking place, maybe we could make better use of the sun's energy. Researchers are looking for answers here, 14 meters under the Earth's surface.
How does it work exactly? With the world's most powerful X-ray laser.
27,000 light flashes per second, and a brilliance that is 1 billion times higher than other conventional X-ray radiation sources. The X-ray flashes are so short that they can be used to film ultra-fast processes in the microcosm. For example, how chemical bonds are formed or released. Here, researchers can observe nature at work.
We are nearly in full user operation. All 6 instrument stations are working. They do experiments, they do fantastic science, and all the users are happy.
The journey of the electrons begins in a so-called particle accelerator and ends here, 3.4 kilometers away, in an experiment hall the size of a football field. During this journey, the electrons in the yellow superconducting modules are accelerated at minus 271 degrees Celsius. The acceleration is so powerful that they reach almost the speed of light after just a few meters. After 2 kilometers, in which the energy of the electrons continues to increase, the tunnel divides step by step into 5 more tunnels.
Here are the so-called undulator systems. 200-meter-long magnetic structures in which intense light flashes with laser properties are generated with the help of electrons. This is X-ray laser light.
An undulator system consists of more than 17,000 individual magnets and guides the accelerated electrons on a slalom course. With each change of direction, they release part of their energy as X-ray flashes. These flashes excite other electrons along the way to emit X-rays as well, and in the process, the incredibly bright X-ray laser light of the European XFEL is generated just like in an avalanche of light.
When an electron flies around a curve, it emits X-rays. These X-ray flashes are eventually separated from the electron beam and guided through stainless steel pipes in the photon tunnels to the underground experiment hall.
Arriving in the experiment hall, the X-ray flashes are not only incredibly bright, but also extremely short. Thanks to the extremely high peak brilliance, scientists can also examine very small samples, and the large number of 20,000 flashes per second mean that the experiments can be carried out faster than with other X-ray lasers. This saves valuable beam time. With the help of these extremely bright flashes, thousands of images are produced which scientists can use to calculate the 3-dimensional structures of molecules and particles.
For me, it's very important that we contribute to answer some of the great challenges of our society, climate change, development of new technologies, development of new medicine. And we will do that by making molecular movies which will use the capabilities of European XFEL.
In addition, chemical reactions can be investigated and atomic details of viruses and cells, for example, revealed. The research goes deep into the microcosm and the nano world. It opens up completely new dimensions and fascinating possibilities. For example, in the field of medicine, novel drugs can be developed if biomolecules and their interactions can be observed with atomic precision. Or for material research, new lightweight materials for tomorrow's aircrafts are examined and analyzed, as are new storage technologies for data.
The applications are unique. Since the very start of user operation in 2017, scientists from across the world come to the facility. Their proposals are selected by committees comprising of international experts.
Their goal? To test new methods, to develop the basis for new therapies, products and procedures, and to establish completely new research fields.
In short, traveling into the microcosm with infinite possibilities.
The world is invited to European XFEL.